In this video, I want to look at determining equations by lines and planes using their points and their normals. To start with, I want to define orthogonal. We say vectors are orthogonal if u dot v is equal to 0. And this is an idea of an extension of the idea of perpendicular. Higher dimensions, perpendicular may not make sense, but we can always define the dot product, so we're going to say orthogonal means your dot product is equal to 0, and it'll be an extension of the idea of perpendicular vectors. As an example, let's consider these two vectors here. If we do u dot v, we would multiply the first coordinate, so -2 times 1, multiply the second, 3 times 2, the third would be 1 times 0, and then finally 4 times -1. So this would be -2 plus 6 plus 0 minus 4, which is equal to 0. So this would be an example of orthogonal vectors. In basic geometry, we learn that a line is determined uniquely by its slope and one of its points. A plane in 3 dimensions is determined uniquely by what's known as its inclination and one of its points. So one way to specify slope and inclination is to use a non-zero vector, which is known as the normal vector. A normal vector is one that is orthogonal to the line or the plane that we're considering. So in 2 dimensions, when we're thinking of a line, we would need a point that we're considering on this line, which I'll denote as x0, y0, and we'll need a normal vector, n, which I'll denote as a, b. So the idea is now I have a point and I have a normal vector. So any vector on the line should be orthogonal to this. So if I consider a vector that starts at x0, y0, and ends at some random point xy, well, then my actual vector here, we'll call it v, would be x minus x0, y minus y0. So this tells us we need n dot v to be equal to 0 since we want these to be orthogonal. So we have ab dot x minus x0, y minus y0 should be equal to 0. So this gives us a times x minus x0 plus b times y minus y0 is equal to 0, and that would be our equation for a line. Similarly, we can get an equation for a plane. A times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal to 0, where x0, y0, and z0 is given by my point, and a, b, c are my components of my normal vector. And these are known as point normal equations of the line and the plane. As an example, let's suppose we want to find the equation of the line that passes through the point 3, -7 and has the normal vector 6, 1. Then we would do 6 times x minus 3 plus 1 y minus -7 is equal to 0. Or 6 times x minus 3 plus y plus 7 is equal to 0. If I want to find the equation of the plane that passes through the point 3, 0, 7 and has the normal vector 4, 2, -5, we would do 4 times x minus 3 plus 2 times y minus 0 minus 5 times z minus 7 is equal to 0. We can rewrite this as 4 times x minus 3 plus 2y minus 5 times z minus 7 equal to 0. And when convenient, we could multiply out these and combine constants to get a more compact form. So this idea leads me to a theorem. The first part of this theorem says if I have constants a and b that are not both 0, an equation of the form ax plus by plus c equal to 0 is going to represent a line with normal AB. So I can look at the coefficients of x and y to determine my normal vector. Similarly, if I have a plane of the form ax plus by plus cz plus d equal to 0, that's going to be a plane with normal vector a, b, c. So I can use the coefficients of x, y, z in order to determine my normal vector. So let's look at an example. The equation ax plus by equal to 0 does represent a line through the origin into space. I want to show that my vector n equal to ab, formed from the coefficients of the equation, is orthogonal to the line. That is, it's orthogonal to every vector along the line. Well, I know that ax plus by is equal to 0. And ax plus by can also be written as a comma b dot x comma y. Well, a dot b is the same thing as n dot xy, which is exactly what I needed to show. So this shows that n is orthogonal to every vector xy on this line. And this can be expanded for higher dimensions as well.